Alright, so let's finish looking at Engel's theorem. This should be the third and final part of this mini-series on Engel's theorem. So to start, we're going to pick up where we left off. And so we just proved the following theorem, which I like to call the common eigenvector formulation of Engel's theorem. So let L be a subalgebra of GL of V for some finite dimensional vector space. If, for all x in L, x is nilpotent, then there exists V that's non-zero element of V such that xV equals 0 for all x in L. And so we prove this by induction on the dimension of L, and we use some various representations. So I restate this theorem because there's actually a related corollary. And I'm not going to present it as it's presented in Humphreys because, first of all, I feel that it could be generalized, and second of all, the proof actually sweeps some technicalities under the rug. So I'm actually going to follow a proof that's a corollary and corresponding proof that's in the MIT lecture notes that was in the description in the previous video, and it will be in the description in this video. So I'm just going to probably copy this verbatim. Let pi be a representation from L into general linear algebra of some vector space. So L is an arbitrary Lie algebra, not the same L as above. And let V be a finite dimensional vector space. So dim V is finite. Suppose for all x in L, pi of x, which is in GL of V, is nilpotent. Then there exists a basis in which all pi of x are strictly upper triangular. Strictly upper triangular. And so the proof of this is once again going to be by induction. And so let's start off with kind of the base case, which is the induction on the dimension of V. So we're going to assume that dimension V is equal to 1. So let me finish writing this. Or on, rather. So if dim V equals 1, right, then all pi of x can be thought of as 1 by 1 matrices, because they're elements of GL of V, which has dimension 1 squared, which is 1. And so if they're nilpotent, the only matrix that's nilpotent, that's 1 by 1, is simply 0. So pi of x are equal to 0, kind of the 0 matrix. All pi of x, right? Because in a field, let's say it wasn't 0, then there's no power of pi of x so that you could get 0, right? A to the n equals 0 only has the solution a equals 0. So the point is that the 0 matrix is strictly upper triangular, and so we're done. Dim V equals 1 is a done and dusted case. So we know this is true. So now we can proceed with dim V being greater than or equal to 2. So dim V greater than or equal to 2. So clearly by this theorem up here, right, if we apply the theorem to pi of L as a subalgebra of GL of V, then we see that we can find a non-zero eigenvector because all the pi of x are nilpotent. So here this is x is nilpotent, but because we're working with the representation, we really are thinking about pi of x. So coming back over here, we see there exists a non-zero V, which I'll call V1, in V such that, so I'll say by theorem, there exists a non-zero V in V such that pi of x acting on V1 equals 0 for all x in L. Now, I want you to consider W as the subspace defined to be the span of V1. This subspace of W is invariant under our representation because pi of W is contained in W, right? In particular, pi of W equals 0, and so that's contained in W. And so because it's invariant, so I'll say W is invariant, we can consider the factor representation of W. So consider the factor representation pi V mod W from L into GL of V mod W. The reason we're doing this is because observe that the dimension of V mod W is less than dim V. So this is kind of edging in the direction of induction. So pi of V mod W, this factor representation, inherits the action of pi of x. So the way it's defined is pi of V mod W for some x in L acting on vectors in V in the quotient space, which kind of look like V plus W, where V is a vector and W is our subspace, which is the span of V1, is equal to, or we'll say defined to be, pi of x acting on V plus W. It sends it to this coset. And so what we immediately notice is that if the pi of x, because the pi of x are nilpotent, the pi V quotient W of x are nilpotent. And that's because they inherit it right here. So I guess what I want to say is that pi V mod x to the n acting on V plus W is equal to pi of x to the n acting on V plus W, like that. And so because it's nilpotent, let's say n is the n that gives us 0, this would equal 0 plus W, and that's the 0 vector in the quotient space. So that implies that this guy's nilpotent. So the whole point of this is to apply the inductive hypothesis, right? We just found a representation, which is the factor representation, on a finite dimensional vector space, which is V quotient W, and where all the elements of that factor representation give nilpotent operators. So that means we can, and because it has dimension less than V, right, V quotient W has dimension less than V, that means by the inductive hypothesis, so I want to be explicitly clear here, there exists a basis of V quotient W in which all pi of V mod W of x are strictly upper triangular. So I want to write it this way, right? Suppose the basis is, this basis is the following. V2 plus W, right, because they're all cosets. V3 plus W, dot, 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 up to Vn plus W, where V2, V3, Vn are vectors in V, right? So this is a basis for V quotient W. And I know there's n minus 1 vectors because dim V, oh yeah, I forgot to mention that. Here, we'll say m. We'll put an m here. and we'll say that dim v equals m, and so dim v mod w is m minus 1, because w has dimension 1. So coming all the way back here, we have this basis for v quotient w, and we're saying that it's strictly upper triangular. So I want to write it out in the following way. Pi of x acting on v1 is equal to 0, right? And that's the v1 that we use to define w, up all the way up here, right? Right here. And we're saying w is the span of v1. So that's kind of the first line here. W equals span v1. Now, pi of v quotient w, the factor representation acting on the first basis vector v2 plus w, because it's strictly upper triangular, right? So what I'm going to assume is that it's strictly upper triangular with v2 plus w being the first column, v3 plus w being the second column, all the way up to vm plus w being the m minus 1th column. Like that's the ordered basis. Yeah, so the basis is ordered this way. And so because this thing is equal to pi of x acting on v2 plus w, right? Because it's strictly upper triangular, this actually has to equal w. So what that's telling us is that pi of x acting on v2 is an element of w, which is equal to span v1. So we have this result here. Pi of x v1 is equal to 0. The 0 vector, that is. Pi of x v2 is an element of the span of v1. And then similarly, because the upper triangular basis for v quotient w, pi of x acting on v3 plus w is equal to pi of x acting on v3 plus w is going to be an element of span w plus v2 plus w, right? Because it's upper triangular. So what this means is that pi of x acting on v3 is an element of span v1, and v2. And if we keep on proceeding this way, what we eventually get is pi v mod w of x on vm plus w is equal to pi of x acting on vm plus w is an element of span w, v2 plus w, dot dot dot, vm minus 1 plus w. I'm out of space there, plus w. And so this implies that pi of x times v3 is an element of span v1, v2, dot dot dot, up to vm minus 1. Oops, and this shouldn't be an m here. That should be a... Sorry, that shouldn't be a 3. That should be an m. So let me erase that. Element of span v1, v2, dot dot dot, up to vm minus 1. And so what we've just done here, right, is that we found this basis for v quotient w in which v quotient w is strictly upper triangular. And then what we realize is that by using the pre-images of these basis vectors, we're seeing that those pre-images, in addition with v1, create a strictly upper triangular basis, or rather create a basis for v in which all the pi of x are strictly upper triangular, right? Because we're saying that this is true for all x. And I guess as a word of caution, I should show that these guys are linearly independent, right? I should show that v1 through vm minus 1 are linearly independent. Well, we know they're linearly independent because the images when we quotient out V1 in the quotient space are already linearly independent, because we know this is a basis. So what we immediately see is that V1 through Vm is a basis for V in which pi of x are all strictly upper triangular. So that's how you prove the corollary. It's a little bit confusing. And it was confusing for me for a long time, because what's really going on is that they're reaching into the quotient space and then finding this basis in which the quotient space is a basis for the quotient space in which all the factor representation are strictly upper triangular. And then because this factor representation kind of inherits the representation of interest, pi, because pi, the factor representation is strictly upper triangular, we can show right here that pi itself is strictly upper triangular with the V1 that we use to quotient out, that we define in terms of W. That's the thing that maps onto 0 under pi of x. So that is the corollary. So now, with that being said, we can actually prove our last theorem of chapter 3, which is known as Engel's theorem in the book, surprisingly enough. And so we need this theorem again in order to prove that. So I'm going to box this and recall this. And so we've actually seen this theorem before. So I think I'll actually move to the left here. Give myself some more space. So we have the following theorem. Let L be a Lie algebra. If all elements of L are ad nilpotent, then L is nilpotent. So at the end of the video on nilpotency, we saw the other direction, and I raised the question, is it true the other way? And so we know that if L is nilpotent, then all its elements are ad nilpotent, and so this theorem is going to use induction very similarly to the previous two proofs to show that L itself must be nilpotent if all of its elements are ad nilpotent. So the way this theorem goes is going to use we're going to kind of use the fact that L quotient its center. If that's nilpotent, then L is nilpotent. So let's dive right into this. So proof by strong induction on dim L. Clearly, if dim L equals 0, this is true, right? All the elements are ad nilpotent because there is the 0 vector, and L is obviously nilpotent, so this is true. If dim L is equal to 1, once again it's true because L would have to be abelian, and the elements would have to be ad nilpotent, right? Because of the second axiom of Lie algebra. So if you bracket x with ax, this is right, because everything in a Lie algebra of one dimension can be written as span of x, right? This is simply ax bracket x is equal to 0. So the elements are all ad nilpotent, L is nilpotent, we see dim L equals 1 works. So now suppose dim L is greater than or equal to 2. So this is what we're going to look at now. So we're saying that all the elements in L are ad nilpotent. So that implies that ad L, a subalgebra of GL of L, is or consists of nilpotent elements. Right? So L consists of ad nilpotent elements, so ad L consists of nilpotent elements. And perhaps, I know it's in an earlier video, but I wanted to say this again. Which is add nilpotent simply means that X is add nilpotent if add X is nilpotent. Alright, so that's just a recap. So we're here. So add L is contained in GL of L, consists of nilpotent elements, right? And it acts on L. So that encourages us to use this theorem over here, right? Add L, or not the corollary, but the theorem. Add L is a subalgebra of GL of L, and L is, we're going to assume, is finite dimensional, as we will throughout most of this course. And so we see that all of the elements are nilpotent, and so that means what we can do is there exists X element of L such that for all elements in add L, so I'm going to write it as add Y acting on X is going to equal 0. So X is the common eigenvector for add Y. And so what this means is that for all Y in L, Y bracket X is equal to 0. So clearly, X is an element of the center, and X is non-zero. So we see that Z of L is non-zero. And this is important because we're going to use induction, and we want to quotient out the center, so if it's non-zero, we get something smaller. So clearly dim L mod the center is less than dim of L. So now the crux of the proof is right here, right? It's L mod the center, which I'm just going to use Z to denote, looks like this. This is a bunch of cosets, L plus Z, L an element of L, right? And so if all the elements in L are add nilpotent, then all of the elements in L mod its center are add nilpotent. And the way to see this is as follows, right? We can just take L plus Z, and we know that that thing bracketed with L prime plus Z for some other thing in L mod Z is equal to L bracket L prime plus Z. So it follows that add of L plus Z to the n acting on L prime plus Z, is equal to add of L to the n acting on L prime plus Z. But we're saying that that L, because it's an element of our Lie algebra L, this thing for some n is going to be 0. So we know that this has to equal 0 plus Z if we chose n right. And so what that's telling us is that add L plus Z is nilpotent. And since L was arbitrary, we get our result here. And so the whole point of all of this, being really thorough here, was to be able to use our inductive hypothesis, right? Because now we know that L mod its center is a Lie algebra. All of its elements are add nilpotent, and because it has dimension less than L, we know that L mod the center is nilpotent. So the conclusion here, scoring all the way down, is L mod Z is nilpotent. But if you remember from the nilpotency video, there's a fact that we proved, which was that if L mod Z is L mod its center is nilpotent, then L is nilpotent. And so we just showed L mod Z is nilpotent, so it follows immediately that L is nilpotent. And so that concludes this theorem. And so all formulations, right, involve some sort of induction on the dimension of L. And this is a really powerful idea. Even more so if you don't remember the proof, is to understand the idea here. In this theorem, in order to find this common eigenvector, we deconstructed L into two pieces, and then we were able to show that we took one piece to be really large, and then we showed that it was easy to work with the other small piece, and we were able to find a common eigenvector. And we did this breaking down so that we could use our strong induction. Similarly, in this corollary, we once again use strong induction on dim V to construct a basis, right? The induction is doing 99% of the work for us. And similarly, here in this theorem, we use induction again to do most of the work for us. We just showed that L mod the center, a smaller unit, is nilpotent, so we can show L is nilpotent. And so this idea is really fundamental, and that's why they're all really related as Engel's theorem. They all rely on this proof by strong induction of some sort. And so some books call one of these Engel's theorem and the others corollaries, and others might swap that. They're all related, and I think this is like the first foray into really using and understanding the algebraic structures here at play. So that should conclude Engel's theorem. I think we will now move on to chapter 4. So thank you for watching this video. I will see you next time.